Oh. Okay, the last topic we want to touch is the last topic we want to touch is multidimensional stuff. So how does the different schemes work in 2 dimensions and 3 dimensions? So let's start with the simplest method, finite difference, and work our way towards more and more complex methods. It's really easy to explain how finite difference works in 2 and 3 dimensions. First of all, I want to say that finite difference is probably the least flexible scheme to generalize in 2D and 3D in terms of what mesh you can work with. So finite difference works best if you have a regular Cartesian mesh. So the mesh for which the grid lines are exactly aligned with the x and y and z directions, right? So this is called a Cartesian mesh. All right. And if you have a Cartesian mesh, then if you want to discretize du dx, du dy, du dz, there is absolutely no difference between a 2 and 3 dimensional case from a 1-dimensional case. Think about it. If you know how to discretize the derivative, the x derivative of at this point in 1D, then you just look into the x direction and there is absolutely no difference, right? So if it's a central difference, you take the right grid point minus the left grid point divided by 2 delta x. It's exactly the same in 2 and 3D. Same in the y direction, right? Except for my +1 is in the y direction. So in this case, I really represent u as a uij, right? So I is in this direction, j is in this direction. Here is, let's say, this is ij. Here is I minus 1j. Here I plus 1j. And here is I j plus 1. And here is I j minus 1. So for example, if I want the x derivative, let's say if I want the y derivative, I would be taking partial u partial y at ij would be approximated by u of ij plus 1 minus ij minus 1 divided by 2 delta x, right? And if you have upwinding or downwinding in the y direction, let's say if the wind blows from up to down, and you want to upwind, so you want to look at the positive y direction, then you would basically approximating this with u of ij plus 1 minus uij divided by delta x. That would be a central, that would be a upwind or one like a biased scheme. So a finite difference is really easy if you have a Cartesian scheme, if you have a Cartesian domain. Okay, if you don't have a Cartesian domain, for example, finite difference can also support what's called the a curvilinear grid. So a grid that is logically Cartesian, which means it is organized still in the ij direction. So you have a ij here, you have a I plus 1j here, I minus 1j, and ij plus 1 here, etc. It's still organized in the logical section, but the grid lines are no longer aligned with x and y directions, but they are curved, curvilinear, right? That's why we call it the curvilinear linear grid. Okay, and in this case, complex finite difference is a bit more complex. It requires you to transform the grid into a Cartesian grid by introducing artificial coordinates. So you have to do a coordinate transformation, right? From from xy to some let's say grid coordinates c and eta. So you have eta as a function of x and y, c as a function of x and y. You also need to figure out the inverse transform. What is x as a function of c and eta? What is the y as a function of c and eta? So once you have these functions, you can do chain rules. You can derive what is the differential equation, right? In the what's called the computational domain. So if you draw, if you look into the space, if you draw c as the x-axis, eta as the y-axis, and you plot the same grids, then it'll be Cartesian mesh. And you have to transform through a chain rule what is the differential equation in the x and y coordinate into a most likely more complex differential equation in the c and eta coordinates, right? So it's a lot of manipulation in the differential equation level, but the underlying numerics of discretizing the differential equation actually stays exactly the same for finite difference, no matter how many dimensions you go to. All right, so that's finite difference. It's probably the most simple in terms of numerics, but the mathematics you have to go through to actually transform the differential equation from its original form to the differential equation in the computational domain. So this is called the computational domain, is often non-trivial, right? So for example, if you have originally the Poisson's equation, partial u square partial x square plus partial square u partial y square equal to f. So you have this equation. You may have to transform it into something like a being a complex function of this kind of a coordinate transforms, a of c eta times partial square u partial c square, right, plus b as a function of c eta partial square u partial c partial eta plus c a function of c and eta partial square u partial eta square equal to f, right? So you have to do a transformation to get an equation like this. But once you get an equation like this, the discretization is actually the same. That's usually what happens when you look at the finite difference code in real applications.